Hello all, welcome to Engineered.AI. Every major CAD vendor claims that generative AI is the future of product development. They promise lighter parts, shorter design cycles, and optimized structural integrity at a click of button. But as mechanical engineers, we know the real world has strict manufacturing limits. In this briefing, we look past the marketing hype and compare traditional parametric modeling against Creo Generative Topology Optimization (GTO). To make this elevation completely objective, we are using a standard heavy suspension mounting assembly as a control model. As you can see from the engineering blueprint, our design boundary constraints are rigid. We have 6 M20 grade 10.9 structural bolt location on vehicle chassis frame, and the suspension bushing eye must withstand a severe combination of 28 kilonewtons vertical load and also a 14 kilonewton lateral load. This gives our AI generative solver a highly realistic structural benchmark to compute against human modeling rules. Now let's look at how a human mechanical engineer approached this problem using traditional CAD logic. Look at the CAD model on the left side. You can see the classic hallmarks of traditional design. To handle the 28 kilonewton vertical load, we rely on geometrical institution, flat uniform 12 steel plates, structured gussets, distribution the stress away from the bushing eye. The standard wells to tie the assembly to the mounting plate. We use pocketing to shave off weight where we can, but our shapes remain fundamentally linear and boxy. On the factory floor, this design is excellent. It is incredibly cost effective to manufacture. Any standard fabrication shop can laser cut these plates and weld them together in minutes, or cut them from a single block on a basic 3-axis CNC mill. However, from the structural efficiency standpoint, a human institution has its limit. We tend to keep the material in low stress zones simply because modeling highly complex organic stress path manually in software like Creo is incredibly time consuming and inefficient. This result is a highly manufacturable part, but one that carries a major weight penalty. Now let's see what happens when we throw our traditional human assumption and pass those exact same structural constraints into Creo Generative Topology Optimization Solver. Looking at the resulting model on the left, the visual difference is immediate and dramatic. The AI doesn't think in terms of flat plates, stranded steel metal, or welding paths. It treats design space as a blank canvas, elevating millions of load paths simultaneously. The algorithm originally grows material only where it is strictly required to handle 28 kilonewton vertical and 14 kilonewton lateral forces. Notice how the Sharpie box edges are replaced by smooth webbed bone-like structures. The material flows continuously from the base to the bushing eye, eliminating the stress concentration points typically found at welded corners. By letting the AI optimize the geometry, we achieve maximum weight reduction and perfect stress distribution. However, it represents a brand new engineering challenge. This organic, high complex shape is practically impossible to fabricate using a standard plate welding or basic 3-axis mill. This web-like structure can only be produced realistically via industrial metal 3D printing. Now let's put both approaches side by side on a scale and look the objective engineering matrices. From pure performance and structural standpoint, Creo Generative Topology Optimization Solver deserves an absolute blowout. The traditional human design bracket came in a heavy baseline of 4.2 kilograms. The AI generative lattice structures shaved that down to an incredible 1.9 kg, which is a massive 54% weight reduction. Even more impressive is the stress dissipation. By running the algorithm directly inside the Creo parametric tree, the AI eliminated sharp corners, dropped peak finite element analysis stress from 185 megapascals to 142 megapascals under the exact same 28 kilonewton load cases. Additionally, the algorithm solver spit out this geometry in under 30 minutes, whereas the manual modeling, pocketing, and checking took an engineer 2 to 3 full working days. But here is where the marketing brochures stop talking and real world manufacturing reality kicks in. The cost matrix. The traditional human bracket can be machined or fabricated anywhere globally for roughly $120 a unit using standard 3-axis CNC machining. The complex webbed titanium lattice generated by AI requires direct metal laser sintering, industrial 3D printing that pushes the cost up to an estimated of $850. This is the core dilemma facing modern product development teams. AI is unmatched at optimizing for new physics, but it is up to human engineers to optimize for production economics. What is our final executive verdict on generative design tools? The takeaway is clear. Generative AI is not here to replace mechanical design engineers. Instead, it is here to completely redefine our starting point. If you treat the algorithm as an autonomous designer and try to manufacture its output directly, you will break your production budget into highly complex, unmentionable geometry. The real competitive edge for engineering teams lies in a hybrid workflow. Leverage tools like Creo Generative topology optimization to quickly discover hidden load paths and explore organic concepts you would never think to sketch manually. Then you step in as the expert. You use your human understanding of manufacturing limitations to clean up, parameterize, and adapt those organic lines into realistic, cost effective design that your local machine shop can actually build. AI handles the physics, the human engineer handles the business. If your organization wants to integrate advanced tools like generative design or automated simulation loops without blowing up your production costs, let's start a conversation. Make sure to hit the subscribe button below. On Engineered.AI, we are committed to helping professional product developers navigate the complex interface of modern design software, PLM system, and artificial intelligence. What manufacturing constraints does your team struggle with most when setting up generative studies in Creo? Let me know in the comment below. I read and reply to all technical discussion. For direct corporate consultancy, process audits, or training inquiries, reach out to me via engineer.ai63@gmail.com. Thank you for watching, and I will see you in next briefing.